Hello and welcome to CSCI 1. Let's get started. And I'm not making this PowerPoint full screen so that I can draw cool things onto it, and I get cooler pens if I don't make it full screen. So yeah, what are we going to do today? I'll first introduce myself and go over all the silly logistical stuff that you need to go over on the first day of class. And then we'll talk about some history and get into this concept of ethics, which is more relevant to computer science than you might think. So we'll talk about that. So first, about me. So my name is Lawton Nichols. Hello. If you never come to office hours, you might want to see my face, so how about I start up Zoom and wave to you? Sure. Hello, this is me. Nice to meet you. So I will stop this. I guess the lighting's horrible in my room, sorry. Let us quit Zoom. And so, I use he, him pronouns. I will respond to, I don't know, Mr. Nichols, Dr. Nichols, Professor Nichols. But I would prefer it if you would just call me by my first name. Call me Lawton, if you feel like it. So, what have I done? I went to Fresno State for my undergrad, so I know a little bit about transferring to there. And I went to UC Santa Barbara for grad school. And I've been here for only one semester. This is the first school year I've been a teacher here. So this is my second semester. And other than doing programming and teaching stuff, I like to do ballroom and social dance, though I've probably forgotten by now. And I like to play guitar as well. And this is my cat. He is a kitten right now. His name is Lonzo. He's named after Alonzo Church, who was the PhD advisor of Alan Turing, but he's really cool, and I encourage you to look at his Wikipedia page. And I also have two beautiful moss balls, which I haven't really given good names yet, so I'll have to think about that. So yeah, thank you in advance for putting up with me. This is going to be a weird semester, but we will get through it together, okay? So let's get to the information that you probably care about. Everything is asynchronous for this class, just to make it clear. I'm going to record every lecture and I'm going to put it up on YouTube for you to watch. And I'm going to try and keep this following schedule. So the first lecture video of the week, we're going to pretend it's like a Tuesday-Thursday class. So the first lecture video will be up by Tuesday at noon, and the second lecture video will be up by Thursday at noon. I'll try to do it earlier, but that is my deadline. And for exams, because obviously we're not in class, I'll give you a 24-hour window to start and take those. But once you click start, they will be a timed exam. So maybe you'll get an hour and 15 minutes for your midterm, for example. So that's how things are going to work in this class. And obviously you should come to office hours, because then we can be synchronous together. Okay? So as far as expectations go, this is not a hard class. It's just a GE. So I'm not going to throw a ton of work at you, but there is going to be a decent amount, especially if you're new to programming. It might take you a while to wrap your mind around what we're doing in this class, and so you might have to give yourself a bit more time than you thought. Okay? So it's going to be fun, though. I can promise that, but it might take a bit of thinking. Programming is a new way of thinking, that is. So yeah, just remember to start early. Don't wait until the last minute, especially on the programming assignments, because those can get tedious if you don't know what you're doing. It does take some trial and error. Okay? And programming is absolutely not about memorizing. It's more like writing recipes. So you can't really memorize and do well on the tests in this class. So that's either good or bad, depending on your mindset. And yeah, I'll just be here to help you as much as I can. Do come to office hours. I'll have plenty of those. So yeah, let's talk about this class. So it's a weird one. It's a critical thinking class. So we're going to have to do a little bit more than programming. So first of all, computational thinking is what you do. It's actually a form of critical thinking. It's what you do when you program. So you think like a computer. Okay? And so and then there's the normal critical thinking stuff that we're going to talk about in this class, like how to make a good argument and convince people. The rules of logic, which are very important because computers use them. And then also things like fallacies. There'll be a fun essay that you write about those. If this was a in-person class, we would have lots of debates, but I will just be debating with myself this semester, I think. And then we'll get into social issues and use our critical thinking skills that we're about to learn to talk about them as they apply to computer science. Okay, so we'll talk about things like ethics, which is going to be the first topic in this class. So yeah, this class is for everyone. Maybe you've already taken a programming class and you just want to get credit for a GE, or you are thinking about maybe being a computer scientist, or you just want to see the big picture. This class is for you. This class is for everybody. Okay? So let's first go to the syllabus, because that's probably what you most care about. So here's our Canvas site. It's going to look a little bit different because I'm the instructor, but this is what you see. So we go to View the Syllabus, click to download, /view, I guess. Let me actually click to view it big. Here we go. So all this stuff, this is just a standard syllabus, I guess. You got the description, the outcomes, the objectives, things like that. The things that you most care about I've summarized here. So you're going to write 6,000 words in this class. I did not make that rule. We have to have a bunch of essays because it's a critical thinking class. So to get the credit, you're going to write 6,000 words, but I'm going to try and split them up into small bite-sized essays. Then there will also be programming assignments. These two things, essays and programming assignments, will make up the bulk of the work in this class. Okay? And yeah, we will be learning some cool programming languages. The first one's called Scratch, and it's a graphical-based programming language where you you have little blocks that you arrange, and you can do cool stuff. Like this might be like a repeat block, and you repeat. If I could spell repeat, and you can put stuff in here that executes things. So like maybe I don't know, you want to have some kind of animation, and so like these blocks all fit beautifully and nicely, and so maybe the first block that you have displays an image on the screen, and then the next block that you add, which fits in perfectly, just like that, and that's your program. Maybe this block moves the image around to a random spot, and so it animates it. And so that's essentially, in a nutshell, what Scratch is. We'll talk about that in the next lecture. It's a fun little programming language, and I think you'll like it. So that's Scratch. And then the other language that you might have heard of is called Python, and that is a line-based programming language. So you're just writing words. So just a bunch of text that the computer will then go and execute and do your bidding. So the first programming language to get us started is graphical. And then the second one is the more normal kind of programming language that you'll be ready for after doing Scratch. Okay? If you've already taken CSCI 40, I will talk about this when I introduce your first programming language, or you've programmed in some form. Please talk to me, because we'll come up with some personalized programming assignments for you that don't bore you to death. Okay? So the grade breakdown, that's probably the most important thing on the syllabus right now that you care about. 30% of your grade is going to be the programming assignments, 30% will be the essays / discussions, if we have any, and 5% of your grade will be from what I call weekly check-in surveys. So I have to take attendance in some form, so weekly check-in surveys will do that for us. So your first one, if we go to this page, you'll just complete this, and I'll have them every week. That's how I take attendance. Okay. Then there'll be one midterm, that's 15%, and then 20% will come from the final. Okay, so pretty normal. I'll talk about dropping scores in a second. I think that's all I want to show here. I'll talk about late work in a little bit. Yeah, I think that's all I wanted to say here. Textbook. You should try and wait to buy the textbook, because I'm not going to require it per se. I think it's a great one to get, and I'm going to recommend it, but maybe you should wait a little bit and see if it'll help you, because I will base the class on this textbook, but I'm not going to ask you to read a chapter and test you on it. So I'll try and summarize the points as best as I can, but if you want to read ahead and know where we're going, this would be a great textbook to buy. So I'm not going to force you to buy it. Okay? So that is that. I've gone over the grade breakdown, so you don't have to buy the book. It will help you with the essays, though, and the exams. I will give out some extra credit over the semester, and I'm not really sure when the final exam is going to be. What I would like to do is make it the Tuesday of finals week. If nothing goes wrong, you can assume that that is the date, okay? I'll give it to you for 24 hours again. Usually when you have a class, like the final time is set because the class time is set. But this is a bit different this semester. So I'm going to try and make the final the Tuesday of finals week. You can just assume that's what it is if I don't tell you otherwise. Okay? Okay, moving on now to late submissions. So I'm going to accept some stuff. I will accept late programming assignments. Don't mind me. And late check-in surveys up until the last day of instruction. So I'm going to give you plenty of time if you miss one. But that will I will give you a penalty of 50%. But I will give you plenty of time to make it up. So that's the trade-off. I will not accept late essays, though. Okay? So that is my late submission policy. And then I'll also drop some lowest scores. Just one kind of score, though. I will drop your 3 lowest programming assignments. So I'm going to force you to do the essays because I'm required to make you write 6,000 words. But your programming assignments, I will drop the 3 lowest ones. Okay? And Canvas, I'm sure you've explored already, but I'm going to provide you links to everything. All the slides that I create and I'm showing to you now, all the notes that I write on them, all the code that I write in class, I'm going to give that all to you, so don't feel like you have to take detailed notes. Even though you can, I guess, watch the lectures again. It's all going to be here, okay? So all that stuff. And yeah, just make sure that you have paid attention to all this stuff. It's useful to read these things. And yeah, let's just keep on moving so we can get to the actual meat of this lecture. Discord is how you'll interact with me and your peers when you have questions. Okay, we're gonna try it this semester because several of you probably already use it. So Discord, I'm going to open it. This is what it looks like. Here we go, here we go. This is our class, and depending on which class you're in, you'll read the welcome thing. This is where you're going to start out. You'll click this to add the student role, click which class you're in, definitely CSCI 1, change your nickname to include at least your last name so I know who you are, and then add your pronouns if you want, and then read this guide to know how to format cool things. But yeah, if you have a public question, you can ask it in the CSCI 1 channel. I think that hopefully makes sense. If you have a private question, you should message me. Sadly, you cannot. I can't message myself, so let me try and message the bot. If you right-click it, you should see a message button, and that is how you can DM me if you have a question that involves giving away answers that you shouldn't share publicly. Okay, so try and ask public questions when you can, so that your peers can help, but don't share lots of code publicly. Use a DM for that. That's a direct message. Okay, so yeah, just use Discord if you can. I strongly encourage you to use it instead of email because my email is a nightmare. And yeah, I'll try and respond quickly within 24 hours on weekdays and 48 hours on weekends. Discord, I belong to several, so you might see me online, but I'm not answering your question. I don't hate you, okay? I'm just doing something else. And I love you, but I won't be your Discord friend, okay? That is that. Come to office hours. They're going to be on Zoom, so there's no excuse for not being able to drive to campus and make it. So check Canvas. There's the link on the homepage for the schedule of office hours and the Zoom link. They're still kind of up in the air because I don't have all the meetings that I know I'm going to have this semester scheduled. So my tentative schedule for my office hours, if you go here to the home page, click it. The tentative schedule is this. So Wednesday, Thursday, and Friday, 3 to 5, 3 to 5, and 4 to 5. Okay, so that is what I think I'm going to have, and click this link to get to my Zoom. We'll see if that stays how it is, okay? You can also make an appointment, of course. Okay, and then the last thing before we get to the real lecture is I just want to encourage you to get help when you need it, because this is a weird class. Programming is difficult, okay, especially when you're starting out. You will probably get stuck on a programming assignment, and I really want you to come and ask for help, because it's programming is something that you should do with a guide, okay, especially when you're starting out. So if you've been stuck for like 30 minutes on a programming assignment, on some problem, and you can't figure out what to do, come to Discord, come to office hours, ask for help. And yeah, just remember that it's my job to help you and get you over whatever is going wrong so that you can hurry up and get stuck on the next thing, okay? Though I do want to warn you and make it be known that if you get stuck for a little bit, like 15 minutes, that's expected. That's exactly what I want, and that's what it takes to become a good programmer, okay? So that is, I think, everything. That's all that I wanted to show you. Let's start now with the meat of the lecture. Usually I will not make the lectures go the full hour and a half or whatever normal time they would be in a real class, so that I can you can work on your programming assignments or your essays in front of me, and I can help you with them. So if this goes long, it's just because I droned on too long at the beginning, so sorry. So let's talk about the history of computer science. I prefer that there. Okay, so a computer is just something that performs a task, right? It performs some kind of computation for you. And what is computation but addition, division, multiplication, subtraction, and abacus? I'm sure I think I made one in elementary school once, but I'm sure you've seen what this is, and you might have used one before. An abacus is technically a computer. It's a tool that helps you perform some computation that you would like to not do yourself on paper. Makes it a bit faster, makes your life easier. So let's consider the abacus as the first thing, the first computer, okay? So that's a bit of a stretch, I know, but let's roll with it. Now, we get to the 1700s, so a big jump in time, where we get to things called binary and formal logic that we will learn about in this class. So a computer thinks in terms of zeros and ones, ons and offs, whereas we, humans, we think in a language of numbers called base 10. You heard of that? I'll go into more detail about this in a future lecture. But base 10 is where you have 10 digits to use. Okay, so we have 10 digits. We think because we have 10 fingers. That's why we use base 10. So we have all the digits from 0 to 9, and that's 10 digits total, to use to make numbers. Computers just have 0 and 1. And so the second you get to 9, you're like, I'm counting. I get to 9, I need to add 1. I don't have enough digits to put something else here. To go from 8 to 9, it's still 1 digit. But the second you go to 10, you have to add a digit, okay, because you ran out. Okay, so that's what base 10 means, just in case you forgot or you didn't think about it. Binary, which is what this is, invented by this beautiful man, is base 2. Binary is base 2, we say, and so it has 2 digits to work with, just 0 and 1. So the second, you can start counting, okay, that's 0, that's 1. What's 2? Well, I don't have enough digits to stay in a 1-digit number, so I gotta add 1. And we get to 1, 0. So this is 2 in binary. Okay? And you can put as many zeros in the front as you would like, just like you can with decimal. And you can keep on going. You can make different kinds of number systems that even include letters. That's called hexadecimal, that we might talk about. But yeah, computers think in zeros and ones, binary. Okay? And the second you go past 1, you have to add numbers, and you get 1, 0, which looks like 10. So it's the joke is, no matter the base, it's always base 10. Right? Because this is 2 for base 2, this is 10 in base 10. So that's my silly joke. And that is the start of computation, because you need zeros and ones. You need to think about computation in terms of them to eventually make a computer. And so let's fast forward to a little over a century later, and we have a man named Charles Babbage, who creates, or partially creates, this thing called an analytical engine. Okay, so this is a computer in its own right, but it's mechanical. So you can, like, I don't know, maybe it's got something that you can wind or something, some little like handle that you can like spin, something like that. And what it can do is you can give it commands and it can execute them for you in order. So maybe the first command was, all right, you entered two numbers, x and y, let's add those. And let's store that in a place called z, because there's memory in this computer. It remembers things. And then maybe, okay, the next command to this analytical engine can be, okay, take the square root of z, because that's hard to do by hand. So we made a machine to do it. Take the square root of z, and maybe put it back in z, and now show whatever z was, like print it out to the user. However it does it. So this is the kind of computation that might be done on the analytical engine. Even though it's mechanical, it can take programs, which are like little recipes, and perform the commands that they ask the engine to obey, to do. Okay, so that is the analytical engine, invented by Charles Babbage. And now let's fast forward like less than a decade, and we have the world's first programmer. So Ada Lovelace worked with Charles Babbage, and we consider her to be the first computer programmer. And she has a really cool life. So her full name is Augusta Ada King, Countess of Lovelace. So she was royalty, which is cool to think about. She was also the one legitimate child of Lord Byron, who had quite a few illegitimate children. So I want her life. She's so cool. And here is the first computer program that was meant to be, I don't know if you can see this, it's meant to be used on the engine. So Babbage's invention. Okay, so that's wonderful. She was the first computer program, and this this was used to compute the Bernoulli numbers, if you've heard of those. So it's something from mathematics. And that was the world's first program, and Ada Lovelace was the world's first computer programmer, which is really fun to think about. Okay, moving on. So we have mechanical computers. We don't have digital ones yet with electricity, because I guess electricity is still a luxury. So we still need to get to the idea of using zeros and ones in computation. And this happens with George Boole here. So in 1854, George Boole invented Boolean algebra, and that's where we notice that, or he noticed, that we can do some cool stuff with 1 and 0 if we consider it to be true and false. Okay, true is 1, 0 is false. We can perform operations on true and false, on these numbers. Like, this is called the AND operation. I'll talk about this in detail later, but 1 and 1 we can say is 1, and then 1 exclusive or 1 we say is 0, and we can build circuits out of this binary representation of true and false. So like A is either true or false, B is either true or false. These are all Boolean variables, we say. And like this does what's known as the AND operation. This does the OR operation, things like that. And we can build circuits to compute an answer. What this is actually doing is, I think it's doing addition. So that's fun to think about. So you can chain a bunch of these, and you could have what's known as an adder. So you can add binary numbers together. And oh man, I mean, we're at the abacus level now, but we can do even more. Okay, so that's the idea. So Boolean algebra kind of paves the way for how computers can execute things. So there's a big jump between, okay, I know binary, to, ooh, I can use binary numbers in a fun way to perform arbitrary computation, which is really cool to think about. All right, moving on, we have the Turing Machine. So again, this is a mathematical thing. It's not on paper. It's not even a machine at this point. So Turing Machine, invented by Alan Turing, very famous man. And what it is it's a mathematical model of computation. So the Turing Machine, is so good It's such a good model that any program that any computer that will ever exist can be modeled. Any program that fits that computer, like my computer right now, with all its fancy features, it can be modeled using a Turing machine, which is fun to think about. It's just a bunch of, like, you have this thing called a tape, and it has little instructions, and it can write to the tape, it can write ones and zeros. I encourage you to look at the Wikipedia page for this, but the Turing machine is a fun little model of computation that Alan Turing invented to try and discover like what computers could do if they existed. Okay? And the same year, a German man named Konrad Zuse, he invented the first digital computer. So Alan was doing more mathematical, theoretical things, and Konrad here was doing more practical things. And this is the first digital computer. It is completely electric, and there are no moving parts. So it's just a bunch of electrical signals being passed around to do things. So digital, if you've heard that word before, what it really means is it's made up of like discrete things. You have either a 0 or a 1 in your places in memory, so it's using binary, which is really on and off, which is really true or false, which is really, if you're going to be an electrical engineer, for example, it's a high voltage or a low voltage. These all are the same thing. They're all equivalent, which is fun to think about. And a digital computer uses Boolean algebra, built up in a fun way, to perform computation very quickly. Okay? And obviously this was pretty slow back in the day, but it still was faster than any human could ever think. So that's the first digital computer. It's giant. Okay? Keep in mind that it's giant because computers are about to shrink with the invention of the transistor. And so, funny enough, this happened at Bell Labs, which is a telephone company. They had quite a lot of R&D money, it seems. So a transistor is tiny, and a transistor can be used to store memory, to perform Boolean algebra operations. Before, you needed to use things called vacuum tubes, and that's the stuff that was used in the Z3. I think it's actually called the Z3 because we were in Europe at the time. So, yeah, the transistor allows you to make computers very small. Okay? If you care, you'll learn about this later if you ever take like a physics class or an electrical engineering class. A transistor can do two things. It's good for two things. It can amplify a signal. So, like, you have a tiny weak signal. It's like, ooh, coming over the radio waves or something. And a transistor can blow that up. It's like, oh, okay, really, this is the signal, and now we can play it on our speakers and actually hear it. Same thing's going on, actually, with a guitar amp, if you know how guitars work. Electric guitars, that is. They plug in. This is my best electric guitar drawing. Here's the neck and the strings. An electric guitar has these things called pickups, which have usually little, at least back in the day, the standard thing to put in there was magnets. And so the wires made of metal, the strings, which are wires made of metal, vibrate over these pickups, which are magnets, and they induce some kind of voltage/current into this wire, which can then be amplified by use of either a transistor, if you have a solid state amp, or if you're fancy and have a tube amp, a vacuum tube. So transistors allow you to have small amplifiers for your guitar, cheap amplifiers as well. So yeah, it can amplify a signal, but that's not actually what we care about with computers. So go away. So the other thing that a transistor is good for is being used as a switch. So that's really useful for us as programmers or computer scientists because the switch can be on or off, 0 or 1. Off or on, I guess. So this is my best horrible diagram. Excuse me. Let's pretend we got a wire, and it's currently off because there's a switch. Oops, I don't need this yet. There's a switch that's currently off. So like if this were on, the current would flow. but it's off right now. And so you can pretend that this box is a transistor. And this is not at all correct, but this is the idea. If you send high enough voltage through a third wire up here, some V for voltage, it causes the switch to go to the on position. And that allows current to flow from over here to over here. And so we have a rainbow pattern now. And so just by controlling this voltage, you can have something in the on or off position. And if you do that on a small scale, you have a computer. Okay? So that's the idea there. Moving on now to the 60s. So back in the day, there was no internet. I'm sure you can imagine. We had this thing that was first invented in 1968 called the ARPANET. And what it did was it connected computers at some point, only 4 of them, at different schools / research institutions. And my grad school was the 3rd node on this network, which is cool to think about. And now suddenly people are researching how to move information across distances. And so how can computers talk to each other? Now that we have them, they're small-ish, how can we make them talk to each other? So that was a very important discovery / line of research, I think you can imagine. So that is the ARPANET. But we have transistors, but we're still making giant computers. We're just making faster giant computers now, because we can squeeze more transistors inside of them. So we haven't really gone into personal computers yet. That happens more in the 70s. So Apple, the company you know and love, or potentially hate, in the 70s, in the mid to late 70s, they started the personal computer craze. So the first computer that they made together was not very widely sold, but it was just the precursor to the Apple II, which was a huge success. So the Apple I helped start this craze. It was invented by Steve Wozniak, and Steve Jobs was the marketer of all this stuff. Okay, and so the rest is history there. And so now we have tiny computers that can talk to each other. I think we have a nice world. So before we move on, I do want to highlight and stress that this is not just a bunch of dudes in computer science. There are quite a few women that made contributions to the computer science field, and I don't have a big enough slide to talk about all of them, so let me give you some greatest hits. We've already talked about Ada, the first programmer. Let's talk about Grace now. So Grace Hopper, actually Rear Admiral Grace Hopper, she was in the Navy. She made this programming language called COBOL and a compiler for it. And that language kind of revolutionized programming. It inspired C, which inspired C++, which inspired C#, which inspired Java, C++ inspired Java, things like that. We have her to thank for modern programming languages, is what I'm trying to say. Margaret Hamilton, on the right, she worked at NASA. She led the team. She didn't just work on the team, she led it. That produced the onboard flight software for the Apollo program. So Apollo 11, them coming back, like all their spacecraft actually working, we have her to thank for that. And here she is standing next to, this is a famous picture, standing next to a printed out version of all the code that they wrote for the lunar lander, I think. So, yeah, we have her to thank for Apollo 11, among other things. So thank you, Margaret. And okay, let's move on to Sophie now. Sophie Wilson helped design the ARM architecture, which if you have a phone, you have to thank her, because every phone these days uses the ARM processor architecture. Most personal computers these days, with the exception of the brand new ones from Apple, they use Intel, or x86 architecture. ARM is like a new contender, and it's really good in the low power realm. So smaller things like phones and tablets are all using ARM processors, and we have Sophie to thank for that. She was very integral in making these processors and designing them. And then finally we have Shafi Goldwasser. So in 2012, she won the highest award that you could win as a computer scientist. It's called the Turing Award, named after someone you know about now. So her work is kind of beyond me, but I encourage you to look at her Wikipedia page. Her cryptography stuff is really cool. There's this thing called fully homomorphic encryption that will probably change the world someday once we can make it fast enough. So that is, I think, all I want to say for the history of computer science. So now you're experts, and we can talk about programming and you'll have some background, or we'll talk about ethics and you'll have some background. So I think the first thing now, the thing that I want to move to is ethics. So that's the first thing that we're going to talk about in this class. So I just want to start you thinking. We're going to talk about this more in a future lecture, the next non-programming lecture. And these are the things that I want you to think about as you leave class today, let's say. So as you virtually leave class. So is it okay to steal food to feed your family? If there's no other way for you to get food, like there's no church you can go to, you're in the middle of nowhere, there's someone you can steal from, though, or a store that you can steal from, if no one else is going to help you. Is it okay to steal to feed your family? So, how in the world are you going to reconcile these contrasting views? Like, is this all right? That's what ethics means. It's the study of what's okay to do. And hint, hint, there's no right answer. You just have to argue your way better, or argue your point well. Okay. So an argument is the kind of thing that we're going to talk about quite in depth in this class in quite a few ways. An argument, a good argument, we have ways to talk about it and argue why that argument is good. So a meta argument about the argument itself. Arguments can be what's known as sound, they can be valid, other things, and these terms, these are what make arguments good, and we'll talk about those. But for now, I just want you to think about this at a high level. Like, how would you justify it? Like, if you say, yes, it's okay, why? If you say, no, it's not okay, why? So, you tell me, and I'm going to make you tell me in your first essay. And this kind of ethical dilemma, these kinds of debates, they also exist in computer science. So, a very strong one that has come up recently is, how much privacy should we have when we're on the internet? There are some governments that like to track their users. We're one of them. So, and there's different spectrums of how much tracking happens. How much privacy should we have from our government, from the websites that we visit, because they can tell things about us. So they can show us ads, for example, which is unfortunate in my view. So how much privacy should we have? And this is something that you'll have to think about when you're writing a future essay, for example. And then finally, a common one that you hear in philosophy classes as well is it okay to kill one person if it means you're going to save 50 others? So like, is that one person okay to kill if you're forced to choose? So there's no right answer again. What do you think? Okay, so let me pull up your assignment. I will be right back. All right, I'm back. So your first assignment is going to be an essay. So you're going to respond to the prompt that is on Canvas. So let me show you it. Dun, dun, dun. Let's see here. No, sorry, week 1. Went too far. So this is the first essay that you'll have. It's a mini essay, so only 250 words. So just respond to this. Respond to the following questions in a short essay. You got to respond to both, and you got to write at least 250 words. Okay, so is it okay to steal to feed your family? And is it right to kill one person if it means that you will save 50? Okay, so explain your answers and mention why you don't agree with the other side. So mention the other side's argument. And there is no right answer, but you still have to give some reasons and argue your points and be convincing. Okay, so that's going to be due on the 19th at 5. So that reminds me of a slide that I forgot to include from another class. So I'll be right back one more time, and then we'll get out of here. Okay, excuse the silly edit, but I forgot to put this slide in these slides. So I do want to say that all assignments in this class, and I want you to plan on this, except for the check-in surveys, because they will be due at like 5:30, just in case there's something else due at 5. Everything is going to be due at 5, okay? 5 p.m., all assignments in this class, so plan on that. This makes sure that I'm awake when things go wrong, and they will go wrong. They always do, because programming is weird. Okay, there will be issues with submissions and things, and I want to be awake so that I can help you. Okay, so everything's going to be due at 5 p.m., and you should plan on that. Okay, I do make one exception though. So if you work full time, or you care for a child, or things like that, that significantly affect the amount of time that you have around 5 p.m., please contact me and I will extend your due dates to midnight. Okay, so just let me know and we'll make that happen. So yeah, your first assignment is going to be due next Tuesday at 5 p.m. Okay, so that's the 19th. That's a Tuesday. And yeah, so go forth, get started, good luck. And yeah, thanks for getting through this first lecture with me. I'll see you in the next one, and that will be a programming lecture. It will be about Scratch, so we'll get started with that, and I'll see you then.